All right, let's test out the algorithm that you just wrote. So let me run it on some arrays here. So here we go. Here's an array, and I see I'm getting back the sorted result. That looks good. Here's another array. Looks like it was able to sort it. Cool. It's working. So just checking over all permutations and returning the one which happens to be in order. So I'm cranking it up to 8 elements. Still seems totally fine. All right. Here's the original array. Here's the sorted array. Keep running a few examples here. Still seems like it's working. Actually, this time there was a couple elements that were tied, so there were 2 permutations that achieved it. Still seems like it's working. Okay, let me crank it up to 10. Uh-oh, now it's okay. It's turning the wheels a little bit. Let's see. Do we have? Looks like we had 2 repeated elements here somewhere. Yeah, 54 and 54. Okay, so there are a couple permutations that ended up being sorted, but we always get one. Okay. But now it's starting to take some time. And so, I mean, it works, but geez, if it's taken this long on 10 elements, that's not good. So let's see. Let's remember how long is factorial actually. So you can define this recursively. Let's say if n equals 1, return 1. Otherwise, return n times fac n minus 1. So let's see. Factorial of 10 is almost 4 million things that it has to check just to sort 10 elements. Doesn't seem very good. Factorial of 11, almost 40 million. Factorial of 12, almost 500 million. Factorial of 13, beyond 1 billion. Okay, like 6 billion. That's not good, okay? Just 13 elements. Man, we usually need to sort way more than that, okay? So we're not going to want to have to check billions of things. That's going to take a really long time. And so, but I also want to think theoretically, like how does this measure up, this time complexity, this factorial time complexity, compared to some other time complexities that we've seen? Because we saw, for example, like the Fibonacci sequence. If I did my naive implementation of that, you know, that was if n equals 1 or n equals 2, return 1. Otherwise, return fib of n minus 1 plus fib of n minus 2. And we saw that this was complexity. This implementation was a complexity of 2 to the n, right? Because the recursion branched off in 2 directions each time. So every time you branch off, you double the amount of things that you're checking. So how does it compare to that? Is the question theoretically. How does our naive sorting algorithm compare? Well, as it turns out, it's actually far worse, even than an exponential algorithm. So what we can say is the following. We can say that for any number a greater than 0, for any base a greater than 0, a to the n is little o of n factorial. Which remember, that means that this is actually lower bounded by n factorial. I can choose a humongous base of my exponent. Eventually, this is going to turn into something that is greater than this for a big enough n. So this is an upper bound for a to the n factorial. So it's even worse than any possible exponent that I can choose. So how do we prove that? I actually do want to prove that. So let's notice the following. So we can write n factorial, you know, if we expand it out, that is 1 times 2 times 3 times ... times, you know, n minus 1 times n, right? So that's one way to define factorial. Well, okay, so let me go ahead and just take the natural log of both sides. So if I take a natural log of n factorial, I get, so what I remember is the natural log of a product of numbers is the sum of the natural logs of those terms. So the natural log of the product of all these numbers is the sum of the natural logs of those numbers. So that would be natural log of 1 plus natural log of 2 plus natural log of 3 plus ... plus natural log of n minus 1 plus natural log of n. All right? So, all right, I turned a product into a sum. How does that help me? Well, here's what I can do next. If I look at this sum, I realize that this is actually a rectangular approximation of an integral. So let me show you what I mean. So I've created a graph here where the area of the sum of these rectangles is equal to the sum here that I'm looking for. So each rectangle has a base of 1 and a height of a natural log of one of these numbers. So the area is just the base times height. Base is 1, so the area is the height. So here we get natural log of 1 plus natural log of 2 plus natural log of 3 plus natural log of 4, so on and so forth. So, and actually I'm making the height of this be, so the natural log of 2 here is actually the height of the bar to the left. Natural log of 1 is 0, that doesn't contribute anything. Okay. Now if I draw the bars like this, what I see is actually that the area under these bars is greater than the area under the curve natural log of x over the same interval. So if I integrate the curve natural log of x over this interval, I will have a quantity which is actually less than the quantity that I'm trying to understand here. So if I can show that even that quantity, which is less than the quantity that I have, destroys, just absolutely crushes my exponential, then I will also have shown that the natural log of factorial crushes by transitivity. So natural log of factorial is even worse than this integral of this curve. So I'm gonna look at the integral of this curve first. All right. So the integral of this curve is going to be, so it's the integral from 1 up to n of natural log of x dx. All right. Now, if you remember your fundamental theorem of calculus, we can find the antiderivative of this and then evaluate it at two places. So antiderivative of natural log of x is actually x natural log of x minus x. So let me just look at that and see if I believe that. So plus some constant, okay. But here we'll make the constant 0. But let's see, so the derivative of this, okay, by the product rule that would be natural log of x plus x over x, so that's plus 1. Natural log of x plus 1 minus 1, okay, plus 0. So that, you see that gives you natural log of x. Okay, so that's the antiderivative. So therefore the integral of this, by the fundamental theorem of calculus, is that would be x natural log of x minus x evaluated at n minus that evaluated at 0. All right, so that turns out to be, so natural log, sorry, evaluated at 1. Okay. So natural log of 1 is 0. Okay, so we get, so this turns out to be n natural log of n minus n minus the quantity 1 natural log of 1, which is 0, minus 1. Okay. So that is going to be just n natural log of n minus n plus 1. Okay. So what I've shown is that so this is actually less than the natural log of n factorial, is what I've just shown. So let me actually raise e to both of these. So I will say e raised to both sides here, that would be e to the n natural log of n minus n plus 1 is less than, well, e raised to the natural log of something is just that thing. So it's less than n factorial. Okay. So now I've converted the expression a little closer to something that I wanted. So e raised to this I've just proved is less than the thing I was trying to analyze. Okay, now I just have to use some rules of exponents. So what I can do is, all right, so the negative n, I can actually pull out each thing here. Okay, so the first rule of exponent I'm going to use, I'm going to say this is e to the n, natural log of n, times e to the negative n times e. That's the first thing I can say. So I split each one of these up. An exponential to sums is a product of the exponential of these individual things. Okay, e to the n natural log of n. So what you can say is that so an exponent to something times something else, that is as if I pulled that one of those factors out and raised that to that factor. So I can write this as e to the natural log of n raised to the n times the rest of that stuff. Okay, so I'm just using more rules of exponents here. Well, e to the natural log of n, again, e raised to the natural log of something. Natural log is the inverse of that. So I just get back that thing. So this simplifies down to just n raised to the n times e to the negative n times e. So what you end up seeing is that I'm going to combine these. E to the negative n is 1 over e to the n. So what you see is that, let me pull these into the same thing together. What you get is that n over e, so e times n over e to the n is less than n factorial. Alright, so remember what I'm trying to show is that any exponent is little o of n factorial. If I show that that exponent is little o of this, then I will have shown that by extension. So let me just review really quickly what I have to do, what the burden of proof is for me. So a function f of n is little o of a function g of n, so is upper bounded strictly by a function g of n if for all constants c greater than 0, we can find a constant n sub c so that f of n is less than that constant times g of n for all n greater than n sub c. All right. So in English, what this is saying is that beyond a certain point, my g of n is going to totally crush f of n. I can scale down my g of n as much as I want. I will still win. So I'm going to ask you to find this constant. But I just want to, given this constant, I'm going to ask you to find this constant. Where does it crush it? Beyond where does it crush it? But I just want to plot some stuff first. So I'm going to plot a raised to the n versus n factorial versus this lower bound of n factorial. So let's look at all of them. And I'm going to plot them on the y-axis. I'm going to plot on a log scale because they grow so quickly. Okay. So what I see here is that it looks like at the beginning 2 to the n is greater than n factorial, and it's also greater than this approximation, this lower bound of n factorial. You can see that that lower bound, it's doing pretty much what the factorial is doing, it's just a little bit less. Okay, but you see they both eventually overtake 2 to the n. Okay, let me make the base a little bit bigger. Okay, now it just takes them a little bit longer to overtake 3 to the n. What if I make it 4 to the n? Okay, it looks like, yeah, I don't know, I'm not sure. It looks like they just kind of tie there. But I can see that this one is not growing. I can just see visually it's not growing as quickly as my factorial and the factorial approximation. So if I just zoom out a little bit and I let n go up to 15, then I see, yes, they're going to beat it. They're going to win. And I can see that the factorial and its approximation are getting really close together. Okay. What about a base of 5? Well, I just have to go a little bit further until I see that. But the point is, I'm always going to be able to find an n beyond which this is larger, okay, for any scale of this exponent. All right, so that's pretty interesting. So anyway, I'm just showing that exponential, or that factorial algorithms are really horrible. They're even worse than exponents. In fact, when we're really busy in the department, Professor Schilling likes to say, I have n factorial things to do today, because that's like practically the worst algorithm that you would ever implement in practice. Okay. But so we're going to move on to more efficient sorting algorithms in a moment.